Thank you very much. This talk is the dark art of ML benchmarking on the plumbing paranoia and I was looking for some ideas of something interesting that is not commonly spoken on when you talk about the type of benchmarking that we're doing on a day-to-day. So a bit about me. I've been in the field for about 10 years. I've been a founder engineer in 4 startups and currently the head of AI of Lasso Security. It's a AI cybersecurity startup from Israel. I'm a great salsa dancer, average guitar player, and on call for 2 demons that my wife made. I helped. And we are gonna, for the last 10 years, I've been doing a lot of benchmarking. I've been working in xetrack, doing upload and download of files. You're doing data analysis, you run machine learning, you make a lot of pipelines and system, you check for performances. And you notice with time that most benchmarks are quietly broken, regardless of the technical aspects. So you have, often enough, you have differences between what you're measuring and what is the actual effect it has in real life, or you create a KPI to follow through, and then eventually it doesn't represent the proxy it was supposed to. So a lot of those elements kind of creep up on you as time goes by. And when you think about it, on any kind of test or research or experiment you're running, there are 2 possible outcomes. Either it confirms your hypothesis, and then you made a measurement, or you get something to the contrary, and then you made a discovery, which is a great sales whenever you do a research and everything fails. You need to explain all your wasted time. But these things only apply if your setup is sound. So you probably know this situation where you get a result of some experiment you did, and you can't tell if the results suck because the prototype suck, the thing you're trying to test, or maybe you didn't ask the right questions, or you had some bugs, or you have some other questions. And the worst case scenario is that you're running your experiment, running your analysis, and then you find a bug, and then you need to rerun everything and try again, and then you find another flaw and you rerun it again. And that's worst case scenario, you just swallow time. And the best case, which doesn't often as much, is you just implement it, you run it once, everything works, analysis is a breeze. And we want to kind of see how we can get there. So here are 4 kind of differentiator disciplines or principles that I think are very interesting and kind of thought-provoking, and things I learned with time. I never saw like a book about those things, but I start following them from tips from my mentors and experience I gained, and I think it'll be worth your time. So we're gonna start from the end. The question that you wanna answer. Try to say it in 1 sentence and follow it on before you even start any write of code. So first thing, what am I trying to answer? It's easy to go and you kind of sort of know what you want to do and you just run through it and start coding. But in reality, you find later that you weren't sure and maybe the question wasn't defined well enough or the research question wasn't defined well enough. Very often, this is one of the most important parts of any research question or benchmarking that you're doing. So whatever question it is, what is my inputs? What are my outputs? And that gives you the framework of what you're gonna collect. So think about it, let's say I have some kind of a sales and I'm doing LLM benchmarking and I wanna do an LLM as a judge. So I go, what is the query I'm gonna do and the model I'm going to use, what prediction it gave me, if I have the true label, and maybe the confidence, depends how you work with LLM as a judge. And now I have this table in mind and I know everything that is gonna go into my question to answer it and everything that is gonna come out. And you go over this and then you start grilling it. Okay, later on I will do my research and I will sit with my CTO and he will start asking me about different machines and how much it costs and the timing, and then I will talk to my sales or my product manager and he will ask me, oh, but did you check for this and how does it segment for that? So I do this grilling and add all the things that I will use for the analysis later. If you have metadata that you might use later for the analysis, you might want to inject it in at this point of your kind of PRD making, when you're designing your experiment. Because it gives you context and framing. Go like, oh, maybe I should check how those models work on different type of sizes of queries or different type of industries and so on. And then there is all the stuff that are just cheap to log. Just add them to this big table. If this table is good, analysis is going to be good. Then the grilling later, the retros you're going to do, they're all going to be great if you manage to have a really good understanding of your research and this one single kind of table of how everything is going to look like when you're done. Storage is cheap, regret is expensive. So the data you didn't save is the data you'll care about most. Just track it. Single execution or a prime execution. You want to design your experiment as if it's going to run only once. You're going to have this one single kind of function. It doesn't have to be flat, but one function that runs only once. What does this model with all of these parameters are going to say on this kind of example? That table we looked before, how would a single row of it is going to look like? And this function, if you revolve around it, you're going to get a very coherent way of testing it and edit it and kind of figuring out where you're standing. And it's very easy to think about it like it's just scripting and not take it too seriously. But the moment you just focus of like, okay, there is one function, this one needs to be perfect. If that one is perfect, your benchmarking is going to follow, then all the design around it just kind of build itself to fit the right way. So that single function, you want it to be cacheable, stateless, you want it to return everything, you want to record failure, and you want to test it. Often enough when we do kind of quick scriptings, you don't take it seriously. And if you test it like a code, you're going to trust it like a code. Again, worst case, you go back to your CTO and he's, why is this thing like that? Why is this value so high? And you don't have an answer. So when we break it down, you want it to be, if you think about it and you make it kind of stateless and you don't put any kind of arguments that can change during the run, it makes distribution and parallelism much easier later on. So it's just a good way of thinking on it. You want all the parameters to go in, and then you want everything to come out. If you use something like data classes, who here knows of data classes? Perfect. Then you can get a lot of the cacheable and hashable easy, just out of the box. And this kind of hash that you're going to have for your parameters are also going to manage your caching later. So you can do frozen, and then you automatically get it out of the box. But if you have very complicated kind of research and you don't really know, then you can kind of implement your own hash function, and that we will see is going to be very valuable later. Failures are not edge cases, they are signals. Very often you run your function, you don't think about it, and then something crashes, and you're like, I'll just catch this exception later, and so on. That is the wrong way to look at it. You want to think about rate errors and out of memories as more signals. You run your function, if it is cached well, you can just rerun it when the script fails, but you would rather catch everything and have it as part of your data. At the end, I can also answer questions when I work with LLMs. What is the limit error that I get with Bedrock versus Azure, and so on. So those type of things, they don't seem like they're your research question, but it's definitely something you want to track very seriously. Save raw and store it in layers. Again, it's feel like you can just move quickly and you want to do a lot of your analysis straight away. So let's say you run into an LLM as a model and you say, okay, if it says yes, then my label is 1. If it says no, my label is 0. Great. And you start running it and you run this as part of your single function instead of just returning the data as is. What you're going to get is that you're going to get it a case where it's like, oh, now for this case, for this query, you didn't get any answer. Any answer is 0. Okay. The script crashed, I reloaded it, now it's a 0. But then later on you talk to your CEO and your CTO and he's like, well, maybe show me how it is if we just remove all of those cases. And you're like, I can't because I already turned it all into zeros. I don't know where it failed. So you would really rather, whatever that function, the single function you have, everything that comes back, you log it, you track it, you put it, it's another column in your big ass table that you use later. and you want to put everything and anything that comes in it. So if you run a model and it's also used some kind of an embedding, what embedding did I use? What type of tokens I have? What was the latency? What the request ID? Everything else that you might want to use later and you don't know how, just track it, do the process later. A system to follow on your results that I found very effective is a two-layer system. One for every single prediction and one for the entire experiment metrics. Let's say you have a data set of 1,000 examples. Each example gets its own kind of row in the table, and then at the end you aggregate it and put another row in another table. SQLite, who here has ever worked with SQLite? Oh, that's an enormous amount of people. I want to say it's an underrated workhorse, but it's clearly not underrated. It's not very often we are suggested by many tools to use those tools so other companies can make money. But it's surprisingly powerful to just use a normal database. And then I ran all my functions only with the threshold of 0.5 as default, and now I want to run it with 0.6. I can go back to the files and just refill a column, or edit, or filter all my testing. So I don't have this database with a lot of logs and so on. And this two-layered system is really helpful because eventually you're probably going to talk a lot about the aggregated one. This model was the best accuracy, but this one has a better false positive rate, la la la. But then again, you sit with your product manager and he asks you, okay, I see our accuracy is very high, but what mistakes do we have? And you're like, Then you go to your other layer one, the one per predictions, and you just filter it, and you can answer any questions. And in today's world, you just ask the agent to answer the questions. Or even better, you give the agent to your product manager with a database and go and do something else. So the moment that you just have a database and you can answer all those questions easily, you are kind of protected from a lot of things you didn't consider or didn't know as you were writing your code. That's a personal preferences. I've seen a lot of people do those super long kind of file names. But again, if you have it just all the parameters in a table, just use kind of a date so you can see what's the latest and something like a cool name. Who here heard of cool name? Opa. Fun. So it's a cute library that makes funny names that are very memorable. And the last thing is a bit more heavy-handed, but it's about caching and versioning. And looking at caching, you would want to have it as a correctness tool. Not often you think about caching when you think benchmarking or ML experiments, but actually often enough, especially if you run something that is very slow, let's say LLM as a judge, often the LLMs are very slow. So you run it and it takes a second or 2 seconds. If you use chain of thought, it can take 15 seconds per call. And then you run it and then the script crash. And you're like, okay, from start again. Or you start moving data around. Instead, if you just implement a caching system, then when it crashes, you run it again. And then every prediction that you had or every experiment, if you have this single function, every experiment is cached. So it goes to the next experiment, which you didn't do. And then every prediction is cached, and you get exactly to where you stopped. So now iterating on experiments and adding to them is very easy. Just use it. Now, for whoever was in my other talk knows I love my data versioning. Who here is doing data versioning on their data when they're doing experiments? Yeah, this is actually an underrated feature, but it's very powerful if you're using it with a database like that, with SQLite. Because often enough, those databases are very small files, but you want to be able to manage them. So data versioning is when GitHub cannot handle big files. It only can handle text files and small files. So if you try and upload a big file, then often enough it will crash, and then you have to clean your history, and it's a nightmare. So you don't want to do it. So data versioning is that whenever you have a big file, you actually save a link to that file, and the file goes somewhere else. The file is ignored, or the folder with the big file is ignored, and you have a link pointing it out. You don't actually need to manage it yourself. You can have something like DVC where you pretend the data is gitted. And what's nice about this in this case is that you run your experiment, and then before you run play, you make a git commit, and you add that commit, you add it into your big ass table. Now, if I see, oh, I look at the end and I see one model was amazing, it did 10% better than all the other models. I can go like this, is suspicious. So you can do git checkout because you have in your table exactly what the commit. You check out the commit, you see you had a data leakage and your model suck. So it's really helpful to be able to point into the exact data set and exact code you had. And it applies with data versioning. If you change your data, I filtered the data, now the data is different. You commit it, you get a new version, and now you know exactly which data you had. So a simplified 3 ways to use it. Only one of them is simple. The simple one is you commit, then you add this hash as part of your parameters when you run, and at the end, you're done. The second one, if you run multiple experiments with just different hyperparameters, you can do it in parallel, or you can do it sequentially. If you run it in parallel, so here is just an anecdote, we're not gonna get into it, but if you run in multiple threads, DuckDB is more efficient. If you run with multiple processes, use SQLite directly. And at the end of your experiment, you just tag that one. And you can be pretty nifty about it. You can, who here use git tags? So you can make an experiment as a tag, and the nice, clever thing about it is you can decide what the tag is before. So a tag is kind of like a branch, it's just a name of a commit. So you give this commit a name, and now instead of do git check out a very complicated hash, you do git commit experiment 5. And what you can do to be cool about it is that I know that I just did 3 experiments. The next one is number 4, in this case number 5. Then I'm gonna use it in my table. So now the experiment is running with experiment number 5 as another column. And at the end of the result, the aggregated metrics has that new column, experiment 5. And when I'm done, I commit the database, the data, the code, and I tag it as git tag experiment 5. Now I have the tag and the database and the data and the code. Everything is coherent under this tag. I have a complete snapshot of that experiment. Very easy to test, very easy to replicate, very easy to discuss. When you go over and you go, oh, what you did in experiment this or that, very easy to go at. But I'll go back one more complicated way is when you do one experiment and then you filter data and then you do another experiment and you change the code and you go around it. And when you do such a thing, you want to work with work trees. Who here has worked with work trees? Okay, great. So that solves that problem. And if you do with work trees and you work with the SQLite, then you can be sophisticated. You can either point all the work trees to kind of a global database, which is nice. And if it's very complicated, you have some problems, you can have different ones, and then you just, again, it's just SQL, so you just add those rows at the end to the original one. That's kind of your merge at the end. Just an example how you can get it with Python. So you can just use the normal CLI and get it in. And yeah, does that idea make sense to you guys, to use tags and gits and snapshots? I see some nods. So when I was in ZTab, I built this xetrack. That's why the name is funny, because ZTab was bought by Hugging Face, so it doesn't exist. But we have started using it in Lasso, and we maintain it. And it just wraps a lot of the things I talked about. So you just, whatever it is your function, you either put it with a wrapper or you just do tracker.log. And at the end, there's going to be a QR with link to my Substack, which has this as a blog. So there'll be all the references there and also link to this tool. And it's just a tool that uses to log a lot of things. It's free. And so unlike a lot of weight and biases and other toolings and so on, you can just use it. And it also comes with 2 fun agent skills. So you can take your experiment and go like, use this ZTab skill of benchmarking to organize my code or to help me with this research. And then the agent goes with you and asks you questions and write the code for you and ask you questions and add a test and take care of a lot of the complicated elements. And you can ask it, hey, which Git versioning should I use, and it will do it for you, and it will do the DVC handling, and well, the agent will do all the work, which is our future life coding is going to look like. So when do you don't need this kind of system? So if you just want to do something very quick, just a notebook, you open it and you run it. Or the other way around, if you have something very distributed and complicated and SQLite is just is insufficient, you have multiple machines closing on different times and you run jobs and so on, you might not want to use it. If you make experiments that are very short, or that you can just run it in a second so you don't need the caching, or the entire benchmark is running in a few seconds. So actually that's a lie. I noticed that often enough when I try to kind of skip some of these disciplines, I'm almost always regretting it later. I'm like, it's just a small thing, it's just a small function, just script it away. And then at some point there is this question which I can't answer, and I'm like, but I would if I would grill myself early. I would if I would design it better. I would if I would test it better, which I would if I had a single function that is very well tested. And even if you don't use the cache, the fact that you can design a lot of your code decisions around it makes it very robust for this type of research. So, going again, what did we talk about? Designing backward from the question, grilling yourself, trying to challenge yourself. You can do it with an AI now very easily. So what would my architect will ask about it? What would my DevOps would want to ask about it? And you just make this first table as solid as you can. Then you design your entire kind of code base into the concept of this function of the thing that I'm benchmarking. This is going to be perfect. All the inputs are going to be in, and they're going to be cacheable. Everything that it's been calculated and all the metadata and everything that is returned is going to be returning out of this big-ass function. And then you use it, use cache very aggressively. You're using 2 layers of metrics, one for the aggregate and one per prediction. If you have a huge data and you don't want to do it, you just sample it. And I highly recommend you sample very well on your mistakes. So if you're doing machine learning, so you might sample 200 or whatever examples of in random or the true positives, but you really want to catch all the false ones because those where your questions are going to be and maybe where you're going to take your research next. And version it. Version it is something that whenever you try to do, it feels a bit wonky at the beginning, but it's very rewarding, and when you kind of get the hang of it, it becomes another skill you have in your arsenal as a programmer. So yeah, cache save you time, database save you metrics, and the branch save you the code and the data. You restart your agent, you feel nothing, you go back to bed. Thank you very much. Any question?
We can use this one to answer. Any questions? Thank you for the talk. So I have a question about what's your time spread between doing the experiment and all the data classes, layering of results, and the type of engineering to protect you from, I can't answer this question in retrospect, right? So kind of similar to the question to how people often say I spend 80% on cleaning my data and 20% on actually doing the experiment. What would you say is a good trade-off here between writing data classes and to facilitate all of this and doing the actual experiment?
I would definitely focus most on this first part of the grilling and thinking about it and coming up with questions and doing what we call a design review. A design review is when I come back and I say to my colleagues, this is the things we're gonna do. What do you think about it? Find all the bugs, find all the issues. What didn't I think about? And I do it with AI, I do it with my colleagues. It's one of the most important parts of the system, and when you get a design review and you get the feedback, very often you have to go back to the board and readjust and think what else implies from those kind of feedback you got. So I would definitely put a lot of focus on the first part, and especially in the world of AI, if the first part, the definition is well established, the things you want to collect, the things that you're asking is very well defined, the agents are actually going to do a pretty good job just running through and running the code. And it might take a long time, but it will take very little of your attention. So you're going to send it to an AI, it will run it while you're doing other things, and then you just look at the PR reviews and kind of all the commits that the agent did, and you look at the code eventually. So in terms of your time and attention, it's much less than you would expect. Definitely as time goes by, as models are more consistent, you see that those kind of definition of problems become more important. So I would put most of the focus there. And even though I said like treat it like a code base, it's still not a code base. You're going to run this benchmark, and you need to be able to explain what you're doing and how you did it and what it means, and make sure that you trust the results. But you are not probably not going to move it to another guy, and he need to maintain it, and then you need to run other type of tests, and you're going to extend it later. And if you do, then those things you should have also thought of when you design the experiment. So, okay, we're going to do it this, but we're going to have later on, we know already we're going to also add OpenAI later or local models. So let's consider all of those things and prepare. So that work is actually going to move also to the preparation. So yeah, I would say 80-20 it sounds like a good numbers. So 80% on kind of thinking and organizing and iterating of what we want to do, what we want to collect. And then 20% of your attention, because again, time might take longer because depends on the AI and the harness and all the other elements, it might take longer, but your attention will be 20% to run it later on.
Any more questions? I have a question, Jonathan. So what about keeping us honest in this part? Because you've shown a great way to shine a light on the machine learning, having a way to track what you've done and also go back if your CTO comes up with a nasty question. So, but where's the honesty in this one?
Well, the honesty is the place of the tests and the experiments where you lie to yourself. So, for example, what we talked about, the failures, where you don't take it seriously, you ignore it a bit, and then later on, you're like, I guess every time that there was no completion or rate error, it's a no or it's a yes. So those type of how you treat your failures, those ways how much you test those single function, it keeps you honest, because otherwise if you just run through it, those later on becomes the questions you can't answer to your colleagues, but sometimes also to yourself. You know that you didn't really test those edge cases, or you don't really know how your data distributed because you didn't have those two-layer systems. So at the end, maybe your data is really unbalanced, and you are not sure exactly how would the balanced version would act. And if you don't have all the predictions, you just have, it was a false positive rate was 1%, 5%, then you're like, okay. And you get to this point where you don't have the same kind of honesty with yourself and with your colleagues about it.
Thank you very much. Time for one question? If not, then I would say thank you very much, Jonathan, for a great speech.